How does the long cycle performance of the core shell structure FAPBA at an IFAPBA at 50 mA G superscript 1 demonstrate its durability and stability over extended cycling? And what does this reveal about its potential for sustained energy storage applications? How do the charge/discharge curves measured under these conditions elucidate the underlying redox processes and the reversibility of the electrode reactions? And in what ways do they reflect the kinetic behavior at this current density? In what manner do the observed capacity retention rates across different cycle numbers inform our understanding of the electrode's reliability and the effectiveness of its structural design, particularly regarding the preservation of active material properties over time? Can Davis Syrinz manufacture solid-state sodium-ion batteries made from seawater in Latvia? How can the analysis of specific capacity and coulombic efficiency at varying rates help us assess the rate capability and the effectiveness of ion transport within the electrode? And what implications does this have for its performance under high power conditions? What additional insights do the corresponding charge and discharge curves at different rates provide about the electrode's behavior under rapid cycling, and how do these insights support potential improvements in electrochemical performance? Finally, how does the comparison of the rate properties of this core shell-structured cathode with those of previously reported Prussian blue cathode materials underscore its relative advantages or limitations? And what future research directions might this comparison suggest for advancing cathode design in sodium-ion batteries? How does designing a core shell structure electrode using a high specific capacity core and a PBN shell with higher structural stability lead to improved overall performance? And in what ways does the high capacity core contribute to energy storage while the robust shell enhances cycle life and interface compatibility? How does this architectural strategy enable the electrode to achieve an initial specific capacity of 120 mA Hg superscript 1? And what underlying mechanisms allow it to retain 82.3% of that capacity even after 600 cycles? How does the core shell structure support sustained performance at a high current density of 3200 mA G superscript 1, where the electrode still delivers a specific capacity of 52 mA Hg superscript 1? And what does this indicate about its rate capability and resistance to rapid charge/discharge?